You have a European plug. The wall socket is American. You do not rewire the building. You use an adapter. That is the adapter pattern. It converts one interface into another so incompatible classes can work together. Every time you integrate a third-party library, you are using this pattern. Adapter pattern. Low-level design. Day 11. The adapter pattern converts the interface of a class into another interface that clients expect. It lets classes work together that could not otherwise because of incompatible interfaces. Think of a real power plug adapter. You have a device with a European plug, but the wall socket is American. The adapter sits in between, translating one plug format to another. The device does not change. The socket does not change. Only the adapter translates between them. In software, imagine your code expects a payment gateway interface with a charge method. But Stripe's SDK has a completely different API with different method names and parameter formats. You create a Stripe adapter that implements your payment gateway interface and internally delegates to Stripe's SDK. Your business logic calls charge. The adapter translates that into Stripe-specific API calls. If you later switch to PayPal, you write a PayPal adapter. Your business logic does not change at all. Only the adapter is different. There are two types of adapters. Class adapter uses inheritance. It extends the adaptee class and implements the target interface simultaneously. This only works in languages with multiple inheritance like C++, or in Java with a class plus interface combo. The adapter inherits the adaptee's implementation and translates it to match the target interface. Object adapter uses composition. The adapter holds a reference to the adaptee and delegates calls to it. This is the preferred approach for several reasons. First, it works in every language, including Go, which has no inheritance at all. Second, it is more flexible because you can swap the wrapped object at runtime. Third, it follows the composition over inheritance principle. The adapter wraps the adaptee, translates method calls, and returns results in the format the client expects. In Go, you define your target interface, create an adapter struct with the adaptee as a field, and implement the interface methods by delegating to the adaptee. Let me show you a real-world example. You are building a payment system. Your application defines a payment gateway interface with a charge method that takes an amount, currency, and card info and returns a transaction result. The Stripe adapter struct holds a Stripe client. Its charge method takes your standard parameters, converts the amount to cents, because Stripe uses cents not dollars, builds a Stripe-specific charge params object, calls Stripe's API, and converts the response back into your ticks and result format. The PayPal adapter does the same thing, but for PayPal's completely different API. It creates a PayPal order object, calls PayPal's create order endpoint, and converts the response. The critical insight is that your process payment function takes a payment gateway interface. It calls charge without knowing or caring whether it is talking to Stripe, PayPal, or any other gateway. You can swap payment providers by changing one line where you create the adapter. Zero changes to any business logic. When should you use the adapter pattern? 4 main scenarios. First, third-party libraries. When you integrate external SDKs or APIs, wrap them behind your own interface. If the library updates or you switch vendors, only the adapter changes. Your code is insulated. Second, legacy code integration. You have an old system with an outdated interface. Instead of rewriting it, create an adapter that bridges the old interface to your new code. This is how companies gradually modernize without big bang rewrites. Third, vendor swapping. Today you use AWS S3 for storage. Tomorrow you might switch to Google Cloud Storage. If your code depends on an adapter behind a storage interface, the switch requires only a new adapter. Fourth, API normalization. Different services return data in different formats. One returns XML, another returns JSON, another returns protocol buffers. Adapters normalize all of these into your internal data model. The rule of thumb is simple. If you cannot change the class because it's third-party or legacy, adapt it. If you can change it because it's your own code, prefer refactoring the interface directly. Adapter is everywhere in production software. First, JDBC drivers in Java. Your code calls connection.execute query. The JDBC driver adapts that call to MySQL's wire protocol or PostgreSQL's protocol or oracles. Different databases, same interface. Second, React component wrappers. Your component renders a map component. Under the hood, an adapter wraps Google Maps, or Mapbox, or Leaflet. Each has a completely different JavaScript API. The adapter normalizes them. Third, logging facades. Your code calls logger.info. The adapter wraps Zap, Logris, or Slog. Swap your logging library without changing a single log statement. Fourth, HTTP clients. Your code calls client.get. The adapter wraps net/HTTP, fast HTTP, or REST. Fifth, cloud storage. Your code calls storage.upload. The adapter wraps AWS S3, GCP Cloud Storage, or Azure Blob. Sixth, message brokers. Your code calls broker.publish. The adapter wraps Kafka, RabbitMQ, or Redis PubSub. The pattern is always the same. Your interface stays stable. The adapter translates to whatever external system you need. In interviews, here are the key questions. Design a payment system that supports multiple gateways. The answer is a payment gateway interface with Stripe adapter, PayPal adapter, and Razorpay adapter. Adding a new gateway means adding one new adapter file. 0 changes to existing code. How to integrate a new third-party API without changing existing code? Create an adapter that wraps the new API behind your existing interface. This directly implies the open-close principle. Know the difference between adapter and similar patterns. Adapter versus facade. Adapter converts one interface to match another. Facade simplifies a complex subsystem behind a single interface. Adapter versus decorator. Adapter changes the interface. Decorator adds new behavior while keeping the same interface. Adapter versus bridge. Adapter is applied after design to make things compatible. Bridge is designed up front to separate abstraction from implementation. The pro tip for interviews is to always mention that adapter follows the open-closed principle. You extend the system with new adapters without modifying existing code. And always prefer composition over inheritance for maximum flexibility. 5 things to remember. The adapter pattern converts one interface into another that clients expect, like a power plug adapter between different socket standards. Always prefer object adapter using composition over class adapter using inheritance. Composition is more flexible, works in every language, and allows runtime swapping. Use adapter for third-party libraries, legacy code, vendor swapping, and API normalization. Wrap external dependencies behind your own interfaces. Real-world examples are everywhere. JDBC drivers, React wrappers, logging facades, cloud storage clients, and payment gateways all use the adapter pattern. And in interviews, know the difference between adapter, facade, decorator, and bridge. Adapter changes the interface, facade simplifies, decorator adds behavior, bridge separates abstraction from implementation.